In control theory, observability is a measure for how well internal states of a system can be inferred by knowledge of its external outputs. The observability and controllability of a system are mathematical duals. The concept of observability was introduced by American-Hungarian engineer Rudolf E. Kalman for linear dynamic systems. Definition: formally, a system is said to be observable if, for any possible sequence of state and control vectors, the current state can be determined in finite time using only the outputs. Less formally, this means that from the system's outputs it is possible to determine the behavior of the entire system. If a system is not observable, this means the current values of some of its states cannot be determined through output sensors. This implies that their value is unknown to the controller. For time-invariant linear systems in the state space representation, there is a convenient test to check if a system is observable. Consider a SISO system with states. If the row rank of the following observability matrix is equal to, then the system is observable. The rationale for this test is that if rows are linearly independent, then each of the states is viewable through linear combinations of the output variables. A module designed to estimate the state of a system from measurements of the outputs is called a state observer, or simply an observer for that system. Observability index: the observability index of a linear time-invariant discrete system is the smallest natural number for which is satisfied that, where detectability a slightly weaker notion than observability is detectability. A system is detectable if all the unstable modes are observable. Continuous time-varying system. Consider the continuous linear time-variant system. Suppose that the matrices are given as well as inputs and outputs for all, then it is possible to determine to within an additive constant vector which lies in the null space of defined by where is the state transition matrix. It is possible to determine a unique if as non-singular. In fact, it is not possible to distinguish the initial state for from that of if is in the null space if. Note that the matrix defined as above has the following properties: is symmetric, is positive semi-definite for, satisfies the linear matrix differential equation, satisfies the equation. Nonlinear case. Given the system, where the state vector, the input vector and the output vector, are to be smooth vector fields, now define the observation space to be the space containing all repeated Lie derivatives. Now the system is observable in if and only if. Note: early criteria for observability in nonlinear dynamic systems were discovered by Griffith and Kumar, Ku, Elliott and Tan, and Singh. Static systems and general topological spaces. Observability may also be characterized for steady-state systems, or more generally, for sets in. Just as observability criteria are used to predict the behavior of Kalman filters or other observers in the dynamic system case, observability criteria for sets in are used to predict the behavior of data reconciliation and other static estimators. In the nonlinear case, observability can be characterized for individual variables, and also for local estimator behavior rather than just global behavior.